All right, hi everyone. We have a cool set of presentations here today for two reasons, I think. First of all, and the more important one is that these are the grad student presentations that we're doing this semester. We have two grad students, James McClung, who's right here, and Neha Srivastava, who's sitting down there, and she'll do the presentation next. And the other reason is that they're both talks in the world of simulation, and I think we kind of have a broad range of topics to talk about, and that will be talked about today, which is kind of nice. It's also something we don't really see all that often in the SSC so far, so I'm kind of excited. All right, yeah, everyone, this is James McClung. He's a PhD student here working with Dr. Kai Krzyzewski, who's also here. And I don't have anything else to say about that besides BGK modes. Go ahead.
Thank you, Rhonda. So hello, everyone. Yes, I'm James McClung. Thanks for coming to the talk. Now I'll sit down so I can actually use a computer. So yes, I'll be talking about two-dimensional BGK modes, as I was usually said. There are many names for these things, and I think the most common one is actually electron hole or ion hole or density hole. And there's like half a dozen other acronyms, and I don't know them all because just the phenomenology of space physics is just so rich. These manifest in many different ways, basically, but I'll be focusing on this one in particular. And I've done this work with these people, so Dr. Kai Krzyzewski, so I have the audience, and then also Dr. Chung-Sung Ng in Alaska, and his student, Matthew Franciscovich. So an outline for this talk, this is slightly out of order from the title, but I'll be starting off with reality and just give a bit of history for this kind of mode. And then I'll go into the theory that we're actually working with, and then I will conclude with the simulations that we did and our results. But first, this is what I'm actually talking about. This is the radial profile of an electron density hole, which is a BGK mode. And I want to point out on the left, this is the origin, i.e. the center of the hole. And the key thing here is it's a hole, right? So we've got a low density, and then it's in the middle of a kind of uniform background. I also might point out this kind of edge enhancement at the rim here. That's that little, well, enhancement at the edge. All right, so history of these things. So in 1957, the authors Bernstein-Greene-Kruskal first solved the Vlasov-Poisson system for nonlinear stationary waves. There had been solutions before using the linearized theory, and I think that resulted in Campen modes, but these are nonlinear, and they did it in 1D, so no magnetic field or anything like that. It's pure, just electrostatic stuff. So Poisson equation. And this equation I'm highlighting here is essentially the equation that they solved. They realized that you could actually solve this, and the way they did it involved the decomposition of the distribution function into trapped and passing electrons. So that was kind of their key insights. And actually, those trapped electrons play a very important role in especially 1D electron holes. Now, these were simulated for a bit. There are many simulations between these two things and other theoretical developments. The first observation was 1979. There was this one observation that resulted in two papers that happened in a Q machine. And what they did was in this Q machine, they had this exciter thing. So they basically excited the electric potential at this one end. That is this line up here. And what that caused was two things, actually. So this line, you see here, there's this big bump. That's just a soliton. And actually, it's the normal kind of KdV kind of soliton. And then they also created an electron hole. So this is that the density plot. And that propagated, and that resulted in this lower line. So now we have still a soliton that is moved, and then the hole is way over here now. So moved even further, so it's going faster. And the one thing I want to point out here is the soliton has been damped, right? So that height that it started with is shorter now. The hole, however, has not been damped. And that's actually a key characteristic of BGK modes, is that they aren't damped. So there were other simulations from there, more theoretical developments, probably more simulations or lab observation and whatnot. But it wasn't until 1994 that these were actually observed in space for the first time. So it was by geotail, which was hanging around in the magnetotail, and they were looking into broadband electrostatic noise. And until this point, none of the satellites had the ability to sample at a high enough frequency to resolve these kinetic scale structures, because these are kinetic scale. So this plot is essentially the first published plot of these observed in space kinetic moves. Now this axis is the electric field, not the density. So you see this, there are these bipolar things. These bipolar blips in the electric field correspond to monopolar humps in the electric potential, which corresponds to a hole in the electron density. That's how this all goes together. So this is observing many electron holes passing by the spacecraft. All right, so more recently, we have some 3D PIC simulations that actually predicted hole creation near reconnection, near areas of reconnection. So that was this Drake et al. Picture, and they found that actually the holes scatter and energize electrons, which electron acceleration is just kind of a broad topic, so it's interesting that holes can play a role in that. This picture is actually a picture. This is a single electron hole here. This is the electric field, so there's this kind of bimodal structure. And these predictions were actually confirmed in a few years later by a different paper with cluster observations. So they actually saw this kind of hole creation near reconnection happening. And later, a few more papers. So there was this cluster and double star observations of ion holes in the upstream solar wind, upstream of the bow shock, and they were coincided with magnetic holes. So that's kind of what this picture is, this top thing. So there's this big, it's a big hole, right? 3,000 kilometers, but that is still small on the scale of space. And then there's these electric fields. We'll get into that. It's just also bimodal. And more recently, this I just thought was cool is, so these holes move. And actually this paper found that you can generate Whistler waves via the Cherenkov radiation, essentially from these holes that are moving so fast. So this top plot shows holes forming in this region, and then they propagate to the left. And as they do that, they create these Whistler waves. So I thought that was cool. And this is happening near the X lines of magnetic reconnection. So you can basically use these holes or the Whistler waves created by them as signatures for when you're near reconnection. So now what we're doing, I guess I and collaborators of mine are extending this work that Chung-San, Ng, and Amitabh Bhattacharjee started in 2005. And they were looking at actually two-dimensional electron holes. So all the ones that I've been talking about so far, almost all of them were one-dimensional. So they're kind of, the profile is along the magnetic field line. These ones are two-dimensional. So now we have a magnetic field coming out at us with respect to this picture. And we have this hole in the middle. And this paper found that to have such a hole, it has to, or the electron distribution function has to depend not just on the energy, otherwise it can't be a localized structure. So you have to include some other dependence. And a year later, they introduced this example. This is just an example of such an electron distribution function that depends on the energy W and also the angular momentum L. So this can be used to solve for an electric potential, and this is actually the form that we are studying. And we're studying it using the plasma simulation code, which has been recently developed largely by Kai Grimshevsky. It's a particle in cell code. You need a particle code, something that can do kinetics to study these modes because they're kinetic. This is a relativistic one. It does all of Maxwell's equations. So it does all the physics that you could need for this. So this is an appropriate choice. So this is where we are. So we're studying this electron distribution function down here. And it is subject to these equations. These equations are actually, the top one here is the Vlasov function or Vlasov equation, just subject to two dimensions, azimuthal symmetry. We have this axial magnetic field, and we have a static neutralizing background of ions. And this has also been normalized to get rid of all those nasty constants. Down here, this is just the Poisson equation. It's electrostatic, so basically Maxwell's equations more or less reduced to this. This -1, that's the ion background. Here's our electron charges. This is the electric potential. So this rho is actually really nasty. I would love to write down what rho is as a function of like the radius. Rho is the charge density here, not the radius. Sorry, psi is the charge density, rho is the radius. So I'd love to write psi as a function of r, but it can't be written analytically, so we actually had to solve for it numerically. And that was actually a pain putting that into PSC because it didn't support arbitrary functions at any point. But anyways, so we're studying these things and we wanted to know two things. So when are they stable? Specifically, what range of magnetic fields are they stable for? And when they're unstable, how do they collapse? What causes their collapse? What do the collapses look like? Our first runs involved a Maxwellianized distribution function. And what I mean by that is at each point in space, particles were sampled from a normal distribution that matched the first 3 moments of the actual distribution function. Those first 3 moments being the density, the bulk flow, and the temperature. This is not actually the true distribution, but it was presumed to be close enough. It's pretty common in codes to sample particles like this because it's the simplest way to do it. And we saw these unexpected oscillations. So I want to focus your attention here on this orange row. This corresponds to B naught equals 1. So what we have at the start, this is the electron density. Now in the middle, this purple circle here, that's the hole. There are fewer electrons here. And then there's a slight orange yellow rim. That's the edge enhancement. So at the start, we have a hole. So that's good. But as we time evolve it, as we move to the right here, at a certain point, the hole fills up. So that's not what we expected. And then more interestingly, the hole comes back after a little while long. And it keeps doing this. The hole keeps filling up and then coming back, and filling up again. So it's oscillating, or it's breathing. So we're trying to figure out why are these holes breathing like this? And then to answer that, I ended up eventually making these phase space plots. So let's look at this red row now. So what's going on here? The horizontal axis is now the radial distance from the center. And the vertical axis is the azimuthal velocity of electrons. So at 0 on this row axis, that corresponds to being in the center of the hole. And you can see there's this white region, there's no red, so that means there are no electrons in this region, which is consistent with there are no electrons in the hole, or very few electrons. And at every other vertical slice, it's actually a normal distribution, because that's how it was initialized. This black line is the mean azimuthal velocity, and you see there's actually, it goes down a little bit. That corresponds to that dependence on the angular momentum that we have to include. So there's a slight clockwise bulk flow in this edge enhanced region. Now, as we time evolve it, what we end up seeing is there's a spike forming. And of course, the hole fills up. So this spike was interesting. So I looked into it a little bit more. And actually, when you look at the exact distribution function, there is a spike in the distribution function and a hole. So we initialized runs according to the exact distribution, and that took a bit of work because PSC had to be extended to support inversion sampling to actually sample from an arbitrary distribution function. But once that was all working, you can see here is at t equals 0, we have a hole and a spike. It's much clearer, and I can hopefully go back and forth just to compare them. So here's before, and then if you initialize it properly, after you get the spike. Of course, the density looks the same. So this is purely a phase space thing.
It is a little hard to see on the screen. Can you just sort of indicate it with cursor?
The spike?
Yeah.
So this, it's clear here. So there's this spike. This is for a weaker magnetic field. Down here is a stronger magnetic field. And notice there doesn't look to be a spike here, and I can get back to that later. But essentially, for certain values of the magnetic field, you get this spike, which is more or less pronounced. So now I can show what these actually look like. So here's the moment runs. So this is that breathing I'm talking about. I think I can move it. How do you right click? Yeah. So this is that just breathing effect. The hole is coming back after it disappears, and then it disappears again. And this is unexpected.
I wonder roughly the time scale of that breathing in and out, doing that.
Good question. We do know, and I will get to that. So now this is the exact run. So there's no breathing, no pulsing, very boring. This is what we wanted. So here's the time scale of the breathing. So these are plots of the electron density at the origin. So just right at the center. So it starts off low, and then actually I'll look at this red line. So this red line is that b equals 1 that I've been showing. So it starts off low, so 0.22 maybe, and then it fills up, and then it comes back, and it fills up again, and then the hole comes back, and then it repeats. So the time scale here, this is electron gyro periods. So that's pretty clearly happening exactly, more or less exactly, one kind of cycle of this, one cycle of breathing per gyro period. Meanwhile, for the exact runs, there is no such behavior. These are doing their own thing. So some are stable, some are unstable. So this is like a useful plot. This is just for other reasons, but this is what we were after. So this spike region, we figured, is related to gyro motion. And this is what's going on. So if you are an electron, right here, say you have an upward velocity that's corresponding to counterclockwise, positive v5, that would put you here. So this is the same electron. Here it is in phase space at this radius, at this velocity, and here it is at this YZ coordinates, and moving in that direction. And then here's the actual magnetic field. So according to just the Lorentz force, if you do, V cross B, you get a force times Q. The force ends up going to the left. This is simple gyro motion. So the particle kind of spins around like this. So if its gyro radius happens to be 1/2 of its distance from the origin, or if its gyro diameter is the distance from the origin, it will just gyrate into the hole, and then it will gyrate back out. And down in phase space, it's basically going from here down to somewhere in this region, and then back out. So basically, I say it as the hole is dual to the spike, if you have a weak enough magnetic field. Because if you have a weak enough magnetic field, then you can have these sufficiently large gyro radii that your hole is smaller than. So that explained what was going on with that breathing. So we could move on to look at the stability. Cut to the chase, it was stable for B naught less than about 2, or sorry, greater than about 2. And it was unstable for the others. And we can see this in this unstable phase, there was something interesting that was going on. This plot doesn't show it, but there's actually an interesting spiral that appears during this phase. And also interestingly, the end state is still an electron hole. It's just slightly filled in. So I would love to know more what's special about this hole. I have some ideas, but I won't be exploring that further, unfortunately. But here's the spiral. that forms. So this is at that kind of the linear phase of the instability. We see these radial arms, hopefully that can be seen in person. It's much easier to see if you look at the azimuthal electric field. So we have these arms, and this kind of double counts the arms, but these do, this is how they look. So the spiral appears and it moves against the electron flow. So this is moving counterclockwise, the electrons are moving clockwise. And if this view continued further, we would see the spiral disappear. So what we explained here is going on is because we have these spikes for these weaker magnetic fields, if you look at a vertical slice, just pick a value of rho and look at the f of v phi for that value of rho, you get this bimodal distribution. So this could be a bump on tail instability. And actually, if you look at this instability, if you do some math with it, you can predict the number of arms and the rotation speed of the spiral. And that's actually useful because if you predict no arms, turns out that happens for B0 of 2 or higher, that is implying that there is no spark, so there is no instability. So that is essentially predicting when we have these unstable modes. So, and this agrees with the simulations. So that is a summary of our research. So basically, we found the stability threshold. We found that if you have a hole, if the magnetic field is weak enough, then you need to have this kind of spike. And if you have this kind of spike, that's a bump on tail instability, and you get these spirals forming, and then it decays. And again, they decay to some other electron hole, which is also probably a VGK load of some kind. It'd be very interesting to know what properties it has that causes it to be stable. But that is all I have time for today. So thank you, and I'm happy to take questions.
Yeah, question for James.
Yes, I have a question. So thinking, I had questions on many of the slides, it's very interesting, so I'm sure I'll circle back with you afterward. But I was wondering, so back to the Vlasov equation that you're solving, I imagine that time dependence is neglected in that?
Yes, it's a steady state solution.
Okay, even though it's steady state, but there was still the breathing though that
We didn't want the breathing.
Oh, yeah, so that's like, that was.
And steady state, if steady state is one thing, but whether or not it's stable or unstable is another thing. And so,
Okay,
but the breathing is not steady state.
yeah, okay.
Where you mentioned that these spiral patterns are kind of you can predict it from theoretical point of view. I know you kind of hit everything under math, but can you walk me through kind of qualitatively what kind of mathematical ideas get you there? So how far I understood was for the given B range, what you go.
So I didn't do the math myself. Actually, it was Dr. Chung-Sang who was looking at this and could turn into another paper. But basically, if you just pick a point, no, I'll actually just move to here. So you pick a point in space and just pretend like that's the only point that matters. So it's a local analysis, and it's just looking at the instability. And I think it essentially is just looking at the like the size of the waves that would form if you kind of constrict it to that radius, to a circle of that radius. Just based on the instability that you form, using this, I guess the standard, bump on tail.
Okay. That feels cool.
That's a good question. I would love to be able to answer that better.
No, that's really cool.
Questions?
I saw the magnetic, sorry,
Go ahead, Ted.
Yeah.
So go ahead.
the spatial scale of the magnetic pole that you showed was like a couple, or like of order thousands of kilometers. Is that the same for, like, what's the spatial scale of electron poles or ion poles?
Okay, yeah, good question. So, it's hard to give it in terms of SI units per se. In space, it's often on the order of kilometers. So kilometers, I think I saw some number, thousands, 13,000 kilometers maybe was the largest I saw. Now, in these simulations, I think what really matters, I'll try to find, oh, these are labeled. Yeah, so the length scale here, these are the electron skin depths. And that in these simulations, that is this 0.005 corresponds to 5 Debye lengths. So these are on the order of Debye lengths or very smaller than the electron skin depth.
Thank you.
So you said there was no oscillations for the, like when you use the exact form of the solution.
Mhm.
So even in that case, however, there is gyro motion, right?
Yes.
So then why is it that only for approximate solutions you observe the oscillations?
Good question. So, the breathing comes from these electrons. These are the bad electrons right here that I'm highlighting with my mouse. We've essentially filled in electrons that shouldn't be there. So when you initialize it with the exact solution, these electrons in the spike, this white region, or similarly this white region, these are the bad electrons that would oscillate into the hole. So there's gyro motion going on everywhere, but not all of the electrons are gyrating into the hole. Some are going to be like doing circles over in this corner. Some might be doing circles around the hole. Some might be entirely within the hole. But importantly is none are out of the hole and gyrate into the hole. So we've removed all the ones that would do that.
Okay, so I'll just ask one last one. So again, the spike, to make sure I understand, so the axes and phase space here, it's rho, it's V5 versus rho.
Yes.
Okay, so then rho again is the radius. So
Yes.
so when you see that white depletion of the density, it's kind of, that is the hole, I guess, at different radii? Or how do we interpret the protrusion of the, like even the upper plots? I guess it's even sharper, like that second row.
Yeah, so the spike is sharper here. It's harder to see the hole itself. Now, the hole itself is not the spike.
Okay,
You can see there's this white region. And I'm pointing on the
yeah.
computer there.
Okay, so that's the actual,
That's
close to the origin.
That's the hole itself.
Okay.
At the origin.
And so then a higher radii though, there's still a depletion, like even up to 0.05,
Right.
there's just that little divot.
Right.
in
And
the
that's
plot space. Okay.
actually why we need, like, this top row looks kind of silly. We have this tiny little hole. But actually you need to essentially include enough of the domain to get the spike, which actually extends quite far out.
Mhm.
And that makes simulating these tricky, but
Does the size of the hole matter? Like if you make it bigger, do you get the same oscillation, or does the oscillation like increase or decrease? Like does the relative size of it impact it?
it does to the extent that if the hole is big enough, really it's more to do with the slope of the spike. So as you increase the magnetic field, the spike slope steepens. So it's kind of obscured by the scales here. But this is a very shallow spike. It extends very far out relative to the hole size. And then as you increase the magnetic field, the spike becomes steeper, and actually I glossed over it, but for high magnetic field, the spike is just consumed by the hole. So this hole is big enough that it contains the gyro motion of all the electrons that might go into it. So once you have a hole that's like bigger than the gyro radius of all your thermal electrons, that's where you're kind of big enough that you don't have the spike, and it's definitely stable.
Not really a question, or maybe, can you go back to the slide where you were showing the electric field, the spiral pattern?
So yes. This one or the,
Or just the still? Okay, yeah, so I was just wondering, like, is this related to like double layer structures with the electron density in the spiral?
I don't think so. I don't know much about double layers.
Me neither do I.
My understanding of double layers is that's kind of when you have, what, 2 layers of electrons or
Or opposite charge.
okay. So you can have like a slope or like a electric potential higher on one side than the other. In 1D, I know, double layers kind of are a different phenomenon, and you can get electron holes associated with double layers, but they're different beasts. I guess in a sense, you could say this is a bunch of radial double layers.
That's what.
I don't really know.
Yeah.
I don't know if that's a useful thing to think about or not, but it seems accurate.
All right, thank you again, James. Now we switch over on to this next speaker, who is Neha Srivastava, who is also a PhD student, same year as James, fifth year student. Who is going to talk to us about some OpenGGCM simulations, and based on that topic, you might also guess that she is working with Jimmy Raven. So I will let you go. I hope I'll think.
Thank you for the introduction. Then an exercise. So yeah, I would be, as the title suggests, I would be talking about the response of solar wind tangential discontinuity particularly. There are other discontinuities relation, but we are focusing more into the tangential discontinuity using the OpenGGCM simulation. So I believe like everyone is a space physics people, so I do not have to explain the magnetosphere physics at all. I'll just briefly discuss that the solar wind variations transfer the mass and momentum into the magnetosphere. The primary process is definitely magnetic reconnection, but there are other processes that could allow the influx of the solar wind plasma into the magnetosphere. And especially during a strong northward cases, and we would be discussing more into that. And solar wind, understanding the solar wind magnetosphere coupling is essential to understand space weather. So the motivation of this study is most often like the emphasis when there's a strong flare or strong CME hitting the earth, it has a strong shock, which definitely triggers like a strong geomagnetic storm and this significant geomagnetic disturbance, and everyone talk about it. But on a daily basis, like every hour or minute, there are multiple discontinuities hitting the magnetosphere, and that still causes some geomagnetic disturbance. And mostly they trigger the impulse-induced substorm, and most of them in the previous observations have been related to the tangential discontinuities, which has high density jump. This is the typical structure of the tangential discontinuity. So it does not allow the plasma flow across the current sheet, and there's no normal IMF component, but the pressure has to be balanced in the upstream and downstream of this structure. Earlier, like this tangential discontinuities are more focused into studying the force shock dynamics and transient events, and because of that, like there have been a lot of studies related to that. But we would be focusing more on the MHD aspect of it, and the motivation. So we'll start with two motivations. There's two aspects of this interaction. Before this discontinuity hits, like has any impact in the magnetosphere, it has to interact with the bow shock. And the second aspect is this has to further interact with the magnetopause. So for the first part, that is the interaction of this with the bow shock, in 1974, like Woke and Oyer did the analytical representation of that, and they mentioned that if there's a discontinuity with density enhancement, it could lead to the inward motion of shock, is as well in this, it intensifies it, and it can generate fast forward shock that can further propagate into the magnetosphere. The same could happen, similar thing happens if there's a density reduction discontinuity, but instead of fast forward shock, it would be a rarefaction wave. And following Walk and Oyer's work, Wu in 1993, they did one-dimensional MHD simulation, but they did not have a combined inner magnetosphere with the global solar wind. So, and however, in 1975, just after like a year after Walk and Oyer, there was a study where Neubauer did the analytical calculation, how this, because when the interaction is head on, yeah, we know it would generate a fast forward shock. But if the interaction is oblique, then it can possibly generate more discontinuities, which aren't talked about much. Later in 2007, Maynard did some case studies and they demonstrated simulation case along with the observation that this type of discontinuity, but they focus more on the density reduction case. So this is one aspect, that is the interaction with the bioshock. Now comes the other aspect. Since this has to propagate somewhere, these then interact with the magnetopause. So what happens in the magnetopause? A lot of earlier studies like keep these two aspects separate, but we feel it's important to correlate them together. So in 1969, before even the study of Walkenauer in 1974, Kaufman and Conradi presented the results like if strong high density discontinuity impacts the magnetopause, it could lead to the bulging in the magnetopause. And this was their representation of it. Following this work, Siebeck in 1990 also mentioned about it. And he said, he talked about that this could possibly be because of the compressional wave which is launched by the impact of the TD, by the impact of this discontinuity with interaction with the upshock and the magnetopause. In 2003, Fairfield et al., they did the observational analysis and found a similar structure happening because of these discontinuity interaction. However, not a lot of focus has been done using a global MHD model. They focus mostly on like the foreshock transient events. So to bridge that gap, we started looking at the MHD simulation of these interactions. So for this study, we focus mostly at like how the inclination of these discontinuities impact the wave generation in the magnetosheet, and what is responsible for these magnetopause deformations. This is the general simulation setup. The solar wind is strongly northward, and velocity, typical solar wind velocity. However, the density goes from solar wind density goes from 6 to 30. It's a jump of factor of 5, which is very high. It occurs not infrequent. One would say this doesn't happen every now and then, but it does occur still. And because of that, the dynamic pressure drastically changes from 1 to 5 nanopascal. So we would be looking at the two aspects. We could be comparing two cases. That is the frontal interaction and the inclined interaction. That is the normal of the discontinuity is whether along the sun outline or it is inclined. So This is, we are looking at the current density profile and at the elliptical plane. On the left is for the frontal interaction. One would assume if the discontinuity hits frontally, the first point of contact would be at the subsolar bow shock and the subsolar magnetopause. So that's what happens. So if let me replay this. So this is the video. In this video, if we see, in this video, this was the initial bow shock boundary and the initial magnetopause boundary. As soon as it happens so quickly, sorry, I should have. If you see this line, this is the fast forward shock. Let me see if I could go back. Yeah, so this means that the discontinuity just touched the bow shock, it launched this fast forward shock, which is propagating into the magnetosphere. And this curve, if you see, if this is the discontinuity, which gets modified because of the draping around the magnetosphere. And this fast forward shock then interacts with the magnetopause. There's also some reflection wave going on, but if we see like just within few seconds, there's another wave which gets propagated into the magnetosphere so quickly. And the trailing edge of this fast forward shock is still like the magnetosphere is way behind as to the leading edge part of the transmitted wave, which goes so faster in the magnetosphere. And then there's like the reflection wave, which further interacts with the modified discontinuity. There's like a cascade wave discontinuity interaction happening in the magnetopause sheet. A similar thing happens in the inclined case as well, but for this case, the first point of contact. So for this case, the first point contact would be at the dawn site. And the discontinuity then propagates from dawn region to dusk region. But in the process, like this is the point that it interacts. There's a fast forward shock, and we see like the transmitted wave in the magnetosphere was very clear in this case because it moves tailward. But in this case, it moves more like anti-sunward and dustward, not just tailward. So it's not very clear in this case, but we'll talk about this later. And then we also see the reflected wave. There's another interesting phenomenon happening in the dusk region, but we'll wait for the next step to talk about this. Now, so we are taking just the still of the previous, the current density profile, and this is the frontal case, and this is how this is what the fast wave we see. If we take a horizontal cut along the sun-earth line and plot it and see how it evolves over time, that is what we're doing here, looking at the temperature and the velocity profile. So this is the point where the fast forward shock propagates into the magnetosheet sheet, and this is where it impinges on the magnetopause boundary. If we look at the velocity profile, there's sudden like increase in the anti-sunward flow, like this was anti-sun, there wasn't any flow, but there's like the increase in the sunward flow specifies that the propagation of this compressional wave in the magnetosphere. And we also see some reflected wave features, and then the interaction with the magnetopause and bow shock that goes on. And eventually, bow shock and magnetopause attains its original shape based on the upstream solar wind. If we look at this similarly, if we look at this case, it's the same thing. We see the fast forward shock, but not the compression way too clearly, here. And if, since like, if we compare these two cases, because the Vx is so high, the anti-sunward flow is so high, the compression in the magnetosphere at the subsolar point is slightly lower in the inclined case as opposed to the frontal case. Now coming to the more dynamic motion, and particularly for the inclined case, the magnetopause, like a lot of things happening in the magnetopause boundary, so we'll focus on that. Coming to that, this is the same total current density profile, and on the right is the velocity. If we, let me replay it again. Yeah, so the same what we have discussed before, the wave generation happens there. But if we focus at this region, there's a large bulge in the magnetopause happening. It happens when the fast forward shock approaches here, it also like a small bulge happens. But when this discontinuity is almost there, just before that, there's like a large protrusion of the magnetopause into the magnetosheet. And if we look at the velocity profile, so this is the point where this fast forward shock comes, and there's like in decrease in the Vy flow. That means the magnetopause is pushed inward and then it expands. So there's like a dynamic motion of magnetopause happening in there. Then if we look at like how, if we take a vertical line cut at in the dusk region and see how the magnetopause boundary changes, this is what we get. And if this is the initial magnetopause boundary, if we can look at this, there's a small, like there's increase in the velocity profile. Because of that, there's like a small bulge in the magnetopause, but the second bulge occurs just before the arrival of the discontinuity, and then eventually the magnetopause attains its original shape. And the bulge, the small scale bulge is of like 0.5 RE, but this one is typically 3 or 4 RE, which is huge in magnetosphere. Now, if we look at that, if we look at what a virtual spacecraft would observe at these specific locations. So on the left side, for this inclined case itself, on the left side, it is initially it was in the magnetosphere, but eventually it went to the solar wind. But before that, we would see all these different discontinuities and interaction. On the right is at the dusk flank, that is -4 and 15 RE. It was at the inner boundary of the magnetopause, and then eventually it goes to, but it also encounters like a brief magnetopause crossing there. And so if we look, this is the dynamic pressure profile. If there's so at this point, there's a sudden increase in the dynamic pressure. The magnetopause boundary is defined by where the dynamic pressure is balanced with the magnetic pressure, and due to increase in the magnetic pressure, the magnetopause would be pushed inward, and then the pressure decreases. But this dynamic pressure goes below than the original dynamic pressure. That's why, which makes the magnetopause to bulge outward more. And when this discontinuity with high density enhancement arrives, there's a strong compression in the magnetopause, and then it goes to its original shape based on the upstream solar wind conditions. Now, these are the conclusions. So, in this study, we are particularly we looked at the solar wind discontinuity with high density variation for frontal and inclined case. And in both the cases, we see some interactions in the magneto sheet and the propagation of the fast mode wave in the magnetosphere. The inclined case is particularly important because it gives large scale magnetopause disturbances. And the inclination of the normal is important in the Dantas plane as opposed to the north-south plane. And the future work, we plan to do some multi-spacecraft validations and also like looking at what is the critical angle for this magnetopause protrusions.
Thank you.
The conditions that you used for the initialization simulation, were those chosen to replicate some event or to like optimize some observable parameter in the simulation? Like how did you choose the?
So to be honest, initially I was just playing, I have been playing around with changing the parameters, but then the parameters I chose here, eventually like we saw this happening in the magnetopause. I have cases for different density variations, but for this, like we saw something happening in the magnetopause, which was interesting. And then we stuck around this, and then the Fairfield, this paper 2003, particularly, they have the similar conditions, which we found quite late. So it was not intentional initially.
I have a related question, I guess. So, when you send the shock on, obviously there's been a solar wind already propagating that way. You have a magnetosphere and whatnot. So, I guess how do you create the magnetosphere?
Oh, so in the model, it has the initial dipole. So, and then you have the solar flux, the F10 something. Then it develops over time. It takes around like few hours to develop the magnetosphere.
You start with nothing.
Start with the dipole, the magnetic dipole.
Great. So you have some like preparatory runtime that you do
Yeah.
to get a steady state magnetosphere before you start introducing.
Yes.
Okay. So I have a question, which is that in the inclined discontinuity case, it seemed like it didn't really transmit that discontinuity past the magnetopause. Is that correct? Why? So like in your kind of first animations that you showed, yeah, I think these two. Yeah, so in this case, you can really see like that fast forward shock like kind of passes through the down shock and then also through the magnetopause. But I didn't really see it go through the magnetopause in this case. Am I missing something? Or does that
It is
happen?
happen, but it is more weaker in this case.
Yeah, why is that?
And it is more into, like, if you see at these motions, it's happening. But it's stronger in the frontal, certainly. So, anything happening in this case would be in the tail region, not in the Dayside. But this is like the impact, this bulge which is happening, it's because of the transmission of that in initial state, but it's still weak.
Okay, yeah, I mean, it almost seems invisible, like.
It's like, if you have like this is a pressure balance structure. If you are consider a balloon, like if you push it
Right.
from any direction, it would like the other direction was trying to expand to balance the pressure. That's what it's trying to do.
And actually, speaking of these animations, I was curious, especially in the head-on case, it almost looks like there's some ringing in the inner magnetosphere, like some of these waves. I don't know if that's physical, and once you get into this region, you see they start launching waves back. Is that anything of interest or just coincidence to the setup?
It happens, but our focus was not entirely on that. So these are the surface waves happening in the magnetosphere. So it occurs and even despite this density jump, so it occurs mostly because of the initial fast forward shock. Even if you have like any variation, magnetic field rotation, or any changes in solar wind would launch. The one study was like only if there's no change in the IMF orientation or any density, maybe perhaps you won't see, but other than that, like in all the cases there is.
So I have two questions. So the first is going to be regarding the inclined shock. So how long does that actually take for the shock to actually go from one end to the other? Do you have like a time scale?
It happens within, starts around 30, from the
Yeah, clock at the top.
33 to 40, 41, 42. So, like 10 minutes.
Okay, so pretty fast. And then during that time, it looks like there's some sunward flows that get kicked up in the magnetosheet. Do you see that in both cases? Like in both cases, are you expecting to see sunward flows in the magnetosheet or?
In the magnetosheet, this would have, but this not.
Okay, so you would see sunward flows just in the
this case,
incline?
yeah.
Okay,
If I increase the incline more, so we did run one simulation where inclination, like the most interesting ones would be the inclinations where the norm is almost perpendicular to the sun earth line. That's when a lot of like core shock people, they look into that. And in that case, like you see a lot of sunward flows, even at the nose of the magnetopause.
because you mentioned you want to eventually compare this with multi-spacecraft observations. I was recently a co-author on a paper by Hadi Mandanian that was looking at sunward flows of the magnetosheet just published, and it actually looks kind of similar to some of the
So-
flows you're seeing here.
The person, my collaborator, David,
Mhm.
he works on he has been working on sunward flows, and he loves to talk about it extensively. And the reason, like initially, the study of this started with understanding hot flow anomalies, but no one ever did MHD simulation. Like everyone stuck with the kinetic or the hybrid simulation. So I don't think I have seen any MHD simulation so far for these sunward flows or anything.
That's cool thing.
So I have two questions. So why did you decide to look at current density profile as opposed to other parameters?
I am looking at other parameters. This is what I'm putting it here because it's very clearly visible. And I didn't want to put every
I
parameter
see.
there.
And then if you could go back to the slide where it shows the bar of the current density profile. Yeah, so there is, it goes from negative to positive. So which direction is the positive then?
The negative I have put, it starts with 0. Negative I have put, this is the magnitude, so it has, this is positive. But the negative I put it just to make these structures more prominent. So I was playing around with the color scale to see where I could make it more prominent.
I see.
While we're on the slide, what is the smaller circle in meant to denote?
It's the ice.
I just put it, it doesn't represent anything. I think this is the inward boundary, that's 2RE, which is the inward boundary of the energy simulation. But no, it does not have any meaning.
That's the location of UNH, right?
Yeah.
Other questions? Thank Neha again. Thank you all for coming. A great graduate student seminar, and hopefully we'll do another one next semester.